Good evening, everybody. Thanks for being here tonight and joining us for the University of Rhode Island Plugged into Energy Research Lecture Series. Tonight we're presenting the second lecture in our two-part 2021 series titled Renewable Energy and Our Electric Grid, focusing on innovation at URI. Tonight we're going to hear about some exciting research underway right here at URI about technological innovations to improve energy efficiency, security, and reliability of our electric grid. We have an excellent roster of speakers from the University of Rhode Island as well as the National Renewable Energy Laboratory, and we'll get to them in just a moment. My name's Kaylin Keene. I coordinate energy literacy programs at URI, including the Energy Fellows program. Before we get started, I'm just going to do a little bit of housekeeping to get everyone oriented. I'd like to take a quick moment to thank our 2021 Terawatt sponsor, Vineyard Wind, for helping to make this programming possible this year. For those of you who are unfamiliar, the University of Rhode Island is Rhode Island's land-grant institution, which means we have a three-pronged mission: teaching, research, and extension. Cooperative Extension is the arm of the university that brings science-based resources out to the public. And land-grant university exists in every state. So we have 5 strategic areas of focus. We have land stewardship, food systems and agriculture, water resources, healthy lifestyles, and energy literacy, which is why we're all here tonight. I'd like to encourage those of you in the audience to put your questions as we go along in the Q&A box, please, not in the chat. We'll do our best to answer each question that comes up, so please throw your questions in there. We'll do some questions possibly after each speaker and then at the end of the program as well. We also will have a brief survey that you'll receive at the end of the program in your inbox. We do read them. The feedback's really useful for us, so please fill that in if you can. This session is being recorded. So if you'd like to share it with friends or colleagues after, or if you've missed other sessions that you'd like to see, you can find them on the URI Cooperative Extension YouTube channel. All right. I'd like to introduce our first speaker of the night. We'll be giving some introductory comments to set the stage for the evening. We're very pleased to have Mary Werner with us. She's the Solar Energy Technologies Lab Program Manager at the National Renewable Energy Laboratory, lovingly known as NREL. So without further ado, Mary, I am going to give you presenter privileges. And you can go ahead and share your screen and get started. Thanks, Mary.
Hello, everyone. Hopefully that worked. Give it a second here. Are you able to see my screen?
Not just yet. We're just seeing you at the moment.
Are you able to see it now? Awesome. Okay, well, hopefully that doesn't. Thank you all very much for having me do some introductory remarks. Renewable energy in the grid and having a stable, secure, and reliable grid of the future is a very important part of what we do at NREL, and work really stems across a lot of different areas. And so I just give a couple of slides to give kind of set the stage for the future conversation. First, just a couple of points on solar in terms of where we're at. We've come a long way in the last decade, and the amount of installations is growing rapidly. We're doubling, tripling, quadrupling the amount of solar on the grid just in the last half a dozen years. We were seeing record-setting times, both in total and times, also in quarter, repeatedly the last several years. And the wonderful thing, I think, is that nearly 100% of our new electric capacity that's being added to the grid each year, the last couple of years, has been solar and wind predominantly. And an example is that a new system is installed every 75 seconds in the US. Just to give a quick snapshot on where we've come from the last decade, you can see on this screen that the costs of installing a solar system a decade ago were 2 to 3 times higher, well, typically 3 times higher than they are today. And so a residential system in 2010 cost around $7.53 per watt. Today, it's closer to $2.71. You look at the bottom left on the utility scale PV, the cost went from $4.75 a watt a decade ago down to under $1 a watt. And it's been under $1 a watt now for the last several years, or right around that area. And if you want to look at the color coding of the bars, shows where the costs are. So you can see if that's in the module, in the inverter, in the hardware to install the system, if it's in the labor to install the system, or if it's in soft costs like land expenses or cost acquisition, things along those lines. We recently released, just in September, a document called the Solar Future Study. I encourage you to go take a look at it if you're interested. The link is on the slide. We spent the last 2 years working hand in hand with the Department of Energy to develop this study. And we basically looked at 3 different scenarios and modeled those based on the 2035 and 2050 targets. And so we have a reference case, which is kind of mainly a no change scenario. So we use EIA data, which is typically quite conservative in terms of electricity demand. We assumed existing policies as of last year, and we assumed just moderate changes in the cost reductions. Then if you go down to the bottom scenario, the decarbonization, the electrification, it's advanced cost reductions. It's assuming high electrification, meaning vehicles shift from gas and diesel to electric, industrial process loads, heat loads shift to electric. And that scenario has a very high electrification use. So just to show kind of where we see the growth happening and where the needs are going to be, you can see in these different cases on the left, you have the 2020, which is our baseline actual data of where the generation capacity was at. And then you can see by 2035, which is the middle 3 bars, the reference case of adding an additional 380 gigawatts, but you can see the color coding of what increases over time. And so if you skip to the 2050 version on the end there, and you look at a strong electrification scenario, that top pink is storage. And so you can see this massive change from 2020, where there's almost no storage on the grid, to a huge amount needed by 2050, along with solar and wind. Those are the predominant generation elements in the grid system in 2050, based on assumptions and scenarios, et cetera, et cetera. From our standpoint, I didn't want to go without saying a little bit about what we do in our portfolio. And so this is our NREL solar strategy in a summary slide. In the middle is our 6 research pathways disguised as wedges. And the top 3 wedges are really focused on, I think, what we're talking about today with a reliable and secure grid and the grid integration of the future that's needed, advanced PV panels, and generation 3 CSP. And then on the bottom in the solar to X category, that's really looking at utilizing solar to create fuels, to create heat, to create the storage needed to achieve a highly reliable grid of the future. And so we looked at this, we developed this a couple of years ago, and before the goals are in place. And so we reevaluated it this year and kind of looked at it from the standpoint of, do we need to change our strategy based on these new goals? And we decided that 6 research pathways are still very critical for success. But what's changed is off on the right here, and that's speed and scale, that we have to accomplish these things in the timeline of 2035 and 2050. So ramping up the speed and scale in materials and manufacturing, affordability, accessibility, reliability and resilience, and the solar to X and solar anywhere. And with that, I will conclude.
Thank you, Mary. I was just wondering, so I encourage folks in the audience, again, if you have questions, please put them in the Q&A. But I just had a quick question for you, Mary. Where in the country have you seen solar to be like the most efficient and cost effective?
Good question. Hawaii is kind of first and foremost because of their electricity costs. And so if you have electricity at 30 cents per kilowatt hour, 40 cents per kilowatt hour market, then solar becomes incredibly a very fast payback. California, we've seen a huge increase in demand in California for 2 reasons, very good solar resource and also fairly high electricity costs, along with their policies there. So we're seeing a large uptick there. Arizona has an excellent solar resource. We're seeing a fair amount of solar going into Arizona in a very low payback scenario. So I would say those areas are high, but other areas are largely from bigger from a policy standpoint. So if a state says we're going to get to zero emission generation by 2030, then they're clearly going to ramp up faster than other states.
All right. Thank you so much. We appreciate you being here. So now I am going to take back the privileges and introduce our next speaker, who is our first speaker from URI. So I'd like to introduce Dr. Hui Lin. He's an assistant professor in the electrical, computer, and biomedical engineering departments at URI. Dr. Lin's going to present his research on preempting damage from cyber attacks on the next generation of power grids, which are known as the smart grid. So, Dr. Lin, I've just given you privileges to present, so you can go ahead and share your screen when you're ready. Thank you.
See me slides okay?
Yep, we can see them. Perfect.
Okay. Well, thank you, Kelly, for the introduction, and everyone. Good evening. It's a really great pleasure to be here and to sharing some of our experiences or research, not from my group, but also that happened in our department and then in our campus as well. So I make the topic a little bit general than the original topic, which is specifically focused on my group. So I'll briefly talking about detection and prevention of cyber physical attacks. That's one type of attacks or cyber attacks that target on the different type of cyber physical system, and of course involving the smart grid which integrate many renewable energy resources. So first things first, what are the cyber physical systems? Let's bring the topic a little bit broad instead of just talking about power grid, because we actually have a more first-hand experiences with the other type of cyber physical system than the power system. This including automobile, medical devices, even some what they call the smart agriculture environment. And of course, the power grid, we all interact with power grid as a power consumer, but not much experiences as a system administrators. And even though those cyber-physical systems has a very different appearances, they actually fall in a very similar physical model. There's a control algorithm which can interacting with some of the physical processes. Again, you can think about those control systems have a different objective in their physical processes. And they all have different type of sensors to collect data from the physical processes. And in this case, they can understand what is going on in the physical processes. If there's an anomaly happened and the control algorithm can use its actuators and either remotely or locally to maintain some of the physical state in the physical processes. So while this control system has been there for so many years, while we put in those control systems into the IP-based or some off-the-shelf or modern computer and communication technology, and this becomes what we call cyber-physical systems. And because those control systems become part of are using the general purpose computer and communication technology, they also unfortunately inherit some of the vulnerability in those environments. And as we can observe in the real incident, as well as in the research communities, the attacks can actually generalize in two different ways. The first way, they'll compromise the data that is sending back from the physical process to the control algorithm. So in this case, control algorithm may have a different view or different opinion on physical processes, which will mislead them into making a wrong decision. And on the other hand, they can also compromise some of the control command setting from the control algorithm to directly changing the state of the physical processes. Just in this case, it's not to maintain a continuous operation, but introducing some of the physical damage. And unfortunately, right now, of course, this is a cyber attack that happens in a different type of cyber physical system, but we can see that some real instances already happened in the smart power grid. This including the most famous one, or probably will know, is that it happened in December 2015. It's happened in Ukrainian power plant, and the cyber attacks has taken down a power grid for like 8 hours, affecting 200,000 residents. And this is also the first cyber attack that we know that has put in the power grid into the outage. Even though you previously probably heard something about that cyber attacks has penetrated into the power grid environment or the other type of cyber physical system, but this is the one that actually causing damage. And also there's a very complicated software malware called Stuxnet that happened in 2010, almost 10 years ago, that putting down some of the nuclear facilities in Iran. And also just in the last year and until now, we have seen several cyber attacks, including the ransomware attacks leading to the shutdown of a major U.S. pipeline system, as well as attacks that put in danger in the Florida water systems. So let's take a look at, in a little bit more abstract way, what the cyber attacks looks like in the power system. So if we make it simple, we have at the bottom part of this slide, we can see that we can see the basic element of a single power system. We have different load unit. The load unit will mainly be the consumer of the power, and then we have generators to hopefully to satisfy the load demand. And the power system, of course, their top priority is to continuously satisfy the load demand. And of course, it happens that generators usually not in the same location, the load unit. So we need some transmission or distribution system to deliver the power from the generators to load demand. And in the one substation, we maybe can find in some of the legacy devices, such as in the field side, we can find in some sensors and breakers. And also we can have in the substation some more intelligent devices. These intelligent devices have some increased computational power using some of the high-speed communication networks. So in this case, it's a control center can monitor and control some of the sensors and breakers at the field site remotely or automatically. And also because of this reason, the attackers can penetrate into those devices that within these communication networks in order to perform some of the attacks. The name of the cyber physical attacks is coming from the fact that it is usually initiated from the cyber component, but the ultimate objective is to causing some of the damage in the physical systems. They usually go to several steps of the cyber physical attacks. First step is try to perform some of the penetration. These control networks or the communication networks used by the control system are not connected directly to the public internet. We have a really, in our domain, we actually have a pretty cool name to describing that dangerous public internet, which we call darknet. And the dark, actually nobody's machines, even your machines at home or machines in our campus, is directly interact with the darknet. They're also operated under a certain type of internet service provider, like the Verizon or the Comcast or the AT&T. Similar things for the communication networks here is that they are running operators isolated from the public internet. So the attackers, the first step is try to do is that they try to establish foothold into the cyber infrastructure. To do that, actually attackers can use in different type of social engineering techniques. One of the most typical example that probably most of you have the real experience is that you're receiving a spamming email containing some of the links that allows you to click on those links. Many of the times, clicking on those links will directly kind of downloading some of the malware in your computer, and in these cases, the attack is kind of putting some foothold in your computer, while your computer is part of these isolated communication networks, so it helps attackers to penetrate into these networks. After the penetration, the attackers need to perform some reconnaissance. They try to intercept in the measurement to estimate the physical state and to understanding how the system is working, which means that attackers need to get an idea how the system is working. This can better to help them to determine what attack strategies they try to do. For example, when we try to maintain some of the electronic devices, we can open some breakers to disconnect the transmission lines, but attackers can do the same things, but with malicious objectives. At last, of course, the execution of the attack is trying to using the same communication networks to issue some of the command, and in these cases, those commands can be corrupted in a legitimate format, but with a malicious content. So this is a general case that we observed in today's power grid, but how the renewable energy resources can affect the cyber attacks. And we already mentioned in the first talk, and also happens in New England as well. We have see a significant shift in the power generation, especially with the amount of solar power, and the amount of coal use has declined from 60% to 4%. And hopefully, to try to distribute the solar to grow another 11 gigawatt in the New England area. The renewable energy resources has a very typical characteristics that it is often distributed, provided by the local consumer. So this changing the role of most of the producer and consumer. In general, the producer is more like some centralized generation unit, and the consumer are distributed load unit like our campus or home environment. But right now, one single unit can play the same role as a producer or consumer, and people call it prosumer. And this type of role can actually making the penetration easier. Like we mentioned before, in the cyber attack, the first step is trying to make the penetration. The reason is that many of the users can play as a third-party generation to participating in the power generation. And this third-party unit can either have a very low level of security protection, or the malicious users can disguise themselves as a legitimate third-party renewable energy resources. This brings a typical example of what we call bring your own device into these communication networks, which can help to more easily put in attackers into part of the communication networks that are used by the power grid. So how we can respond? And unfortunately, right now, the research in the cyber physical security is still very challenging. There are some big gaps around in the different disciplines. And right now, I'm just listing two of them. One is the computer engineering, computer science discipline. There are some cybersecurity research for many years, of course. However, cybersecurity research only focuses on some cyber threat in the IT domain, and ignoring there are some physical constraint on those physical processes on the power system. And on the other hand, power engineering domain or discipline or their community have also tried to solve some of the problem on the cybersecurity. They can focus really on a very strong theoretical formulation, but they usually have very little knowledge thinking about what type of vulnerability or what type of software to be used by the power engineering power grid. In these cases, making some of the probably theoretical derivation less effective or less practical in practice. And also, according to my own investigation, only 3% in the university I'm talking about, I'm using the US ranking as the top 100 university in the US, and I investigated both the electrical engineering as well as computer science department. I find that only 3% of those departments providing the related education resources for the next generation engineering workforce. Fortunately, URI has launched several series of cybersecurity courses or education in multiple levels. I'm only because due to as I'm also comparatively new to the URI, and if I didn't include in the other type of department, I'll be happy to include in my future talk. But in our department, we have two courses. One is for the 100 level courses open for all undergraduate students in the campus. Is a grand challenge course called Cyber Physical Security. And this year, actually, this course has 80 students registered, which coming from almost 30 different type of areas. And then there's another more advanced cyber physical security courses, more focused on the current research resources that is created by myself, and try to introduce some of the practical approaches for the students. In addition to that, we also have a cyber center to performing some of the exciting projects leading by different type of professors, so we can group in our research together. This including towards a reliable and resilient smart grid, leading by Dr. He, who will use some leverage some digital twin for the power grid to provide some runtime monitoring analysis. And Dr. Wei and Dr. Yang has tried to propose some of the protection on the hardware malware, because the software can be very vulnerable and can be very different. But ultimately, they were changing the hardware to performing some of the attacks. Based on this objective, they try to provide some of the smart sensors in the computer hardware to track the traces. The last one is led by working in my group is what we call preemptive damage prevention in power grid. Because my understanding is that different from the cyber attacks and general purpose computer system, I hope that we will not only be able to detect the attack, but also preventing the damage. But how to do that is actually more like some, in this case, is provide a little bit more information, like setting a trap for the attackers. We're not trying to detect the attacks after the performing the malicious operation. We try to disrupt the attack's reconnaissance and providing some of the misleading information to the attacker. So in these cases, the attacks designed by the attacker will be ineffective. For example, of course, we need to overcome several challenges, like injecting information needs to be realistic and it should not disturb the legitimate operation. But the ultimate objective is try to mislead the adversary. Using this as a very simple example is like if we have 3 generators, and if we providing this wrong information, like we show in the right bottom of the slide, and attackers will follow his logic to attacking a larger generators, he will end up just disrupting very small generators, which in most of the cases, even if it's successful, in most of the cases is tolerable by the power system. So right now, this is, of course, very small, brief introduction, and also limited to our department, how we performing the researches and providing the educational resources for different type of students and also researchers. So that actually generated my talks, and I like happy taking some questions, and here my contact information if you need if you're interested to learn more.
Thank you so much, Dr. Lin. I think we've all heard a lot about cyber security attacks and ransomware attacks, but not in relation to our electric grid. And I think it's a really important thing for people to be aware of. We did get a few questions, so I'd like to ask one of them now, just before we transition to Dr. Lucht. We have a question from Patricia. Why couldn't the power grid use their own intranet and thereby not be on the internet and susceptible to these types of attacks?
So if I understand the question correctly, I think the question is like, why we putting the power system isolated from the internet? I think that's actually the general design for most of the enterprise system, not just in the power system. Because public internet is open to all the users, and our personal experience is that if you expose your machines to the public internet, you actually continuously receiving different type of attacks. That happens more frequently than we can imagine. And while we isolating the power grid from the public internet, and in these cases, more like some kind of a working in like a local area networks. In these cases, some of the general techniques like the VPN or firewalls can filter in out those information to the public internet. But this does not mean that the power system, the network used by the power system, losing its functionalities as we use in the internet. They're still using the same technology. It's just like the communication between the networks used by power system, as well as the between these networks to the public internet. They have some kind of intermediate procedure to preventing some of the malicious information going through to this network environment.
All right, thank you so much, Dr. Lin. That was very interesting. We have a few other questions for you, but I'd like to move on to our next presenter, and we'll get to those questions at the end if we have time. All right, I'd now like to introduce Dr. Brett Lucht. He's a professor in the Department of Chemistry at URI. Dr. Lucht's research interests focus on the investigation of non-aqueous electrolytes for lithium-ion batteries for use in electric vehicles. All right, Dr. Lucht, I've passed the ball to you, so you can go ahead and share your screen.
Okay, here we go. Thank you very much for the opportunity to talk about the work that we're doing and also the research in the group. Let me go back to that, sorry. Research on grid scale energy storage. And so basically, lithium-ion batteries have become ubiquitous in society. They've really been pretty widely utilized for various applications, including what happened there? Our laptop computers, which many of you are probably watching me on right now, along with cell phones, smartphones. These were basically two of the earliest places we started seeing lithium-ion batteries. And then, of course, now they're starting to appear more in power tools, where there's a lot of cordless power tools. And, of course, in electric vehicles, such as the Tesla, and also now more recently being developed in larger energy storage systems, such as this one displayed here for grid scale storage. So first off, we'll quickly kind of mention why lithium-ion batteries are of such great interest. And there's basically two reasons. One, if you look at the periodic chart, lithium is the strongest reducing element that there is. So in terms of the electrochemical potential, there is no element that has more of electrochemical potential window than lithium. At the same point, lithium is also very light. And so if you compare the energy density, the gravimetric or volumetric energy density of the lithium-ion battery compared to other rechargeable battery systems, such as lead acid, which is the battery that's in your car, NiCad or nickel metal hydrides, which are more of the older generations of rechargeable battery systems, lithium-ion has the most energy storage per unit space or unit mass. And so that's really why lithium-ion batteries are of such great interest for consumer electronics products, laptops and cell phones, because they're small and they're light, and also why they're so important for electric vehicles, because once again, both size and weight are very critical. At this point, they have been introduced into the grid where, size and mass is not as big of an issue. I think a lot of the reason you're seeing lithium-ion implemented into the grid right now is due to availability and some other issues we'll bring up in a little while. So basically, what are lithium-ion batteries and how do they work? And so basically, a lithium-ion battery typically has a lithiated metal oxide cathode along with a graphite anode, which is where the lithium ions go back and forth when you charge and discharge the battery. And they're separated by an electrolyte, which is usually a liquid in most all commercial lithium-ion batteries. And the first time that you charge the battery, the electrolyte is not really stable to the surface of the anode when you charge the battery, and the battery decomposes to generate an interface on the surface of the graphite, which is referred to as a solid electrolyte interface. This interface is what allows the battery to be rechargeable reversibly. And what we've spent a lot of time in my research group studying is the stability of this interface, of this solid electrolyte interface. Because many of you own laptops, as I just said, and also cell phones, and you've probably realized that the cell phone that you have today, the battery lasts much longer than the cell phone that you had 5 years ago or 8 years ago or 10 years ago, or in terms of the calendar life, how many years it lasts before you need to replace it. And the reason that those older scale batteries didn't work as well was this interface generated on the anode isn't very stable. And as you cycle the battery, the initial species which are generated decompose. And not only do they decompose, but they become components of the liquid or gases, which makes the surface film porous, which allows more of the electrolyte to get to the surface of the anode and cause more decomposition reactions, making the surface film thicker and thicker and also more resistant. So many of you have probably noticed in your old laptops, when you use it and the battery doesn't charge very well or dies really quickly, that the battery or the laptop itself gets really hot under lap. And that's partially because this surface film is getting thicker and thicker and it's getting more resistive. And when you're charging and discharging the battery, it dissipates more heat. So what researchers have done was they developed a series of additives for the electrolyte, which generate a different structure of the surface film. The surface film is more stable, and the batteries have a longer calendar life. So instead of only lasting 2 years, 1 or 2 years, like old cell phones did, now your cell phone batteries will last 5 or 6 years, or your electric vehicle battery, which is really critical for this, will last 8 to 10 years, which is a requirement for electric vehicle usage. This is also really important for grid scale storage because calendar life of batteries is really a critical component of the use of batteries in grid scale storage, because grid scale storage is extremely large and also very expensive. And so therefore you need a system that's going to last a very long time. So with this, kind of quickly going over some of the advantages and the disadvantages in general of lithium-ion batteries. As I said, lithium-ion batteries have got the highest energy density of rechargeable battery systems. So in any kind of portable-based power, this is what you want because you want your device to be very light. Lithium-ion batteries also have very low self-discharge, high efficiency, good calendar life, and can also be used for deep discharge, regular, repeated deep discharges. This is really important for things such as grid scale storage, where some systems you can't fully discharge and recharge fully without problems. It's also really critical to not have a high self-discharge, because in a high self-discharge, the battery will just kind of have side reactions, which allow the charged battery to lose energy. Usually when you lose energy, you're also giving up power or energy. The other big problem, or the biggest problem with lithium-ion batteries is the cost. They're very high cost, especially if you're utilizing cobalt-containing cathode materials. Cobalt's a pretty rare metal, which is also expensive, also toxic. And what's usually done, especially for grid-scale storage systems, is lithium-ion batteries are usually used with iron-based cathode materials, which are significantly lower cost, but still, fairly high cost compared to other battery systems. And the thing you want to point out in terms of other systems perhaps being better in the long run over time than lithium-ion batteries for grid scale is that energy density is really not critical for grid scale storage, because you can have large warehouses filled with battery systems. The weight doesn't really matter. The size doesn't really matter because you're not trying to move the system around. So, currently, what kinds of battery storage systems are in use? So this is a relatively recent study by the U.S. Department of Energy, basically looking at all of the different systems that have been incorporated for grid scale storage. And what you can see is that currently lithium-ion dominates the overall grid scale storage systems, and big basically trailers like you saw in the first depiction, which basically these things can be moved around, fairly easily, but then when they're stationary, they can be charged and discharged and used to basically do various things in order to help the grid out. So what are the key characteristics of these battery storage systems? So first off, it's the rated power capacity. So the power of the system is related to rate. So therefore, you can think about this in terms of acceleration of the car. A car that has good power has got good acceleration. This can be important for very many applications for grid storage. Energy capacity is more so the overall the energy of the battery, which is related to how far you can drive a car. Say the car can go a long distance because you have a lot of energy in the car. Once again, another really critical thing for grid scale storage is both cycle life and lifetime, how long these battery systems last, which is really related to cost. Because if a system lasts 20 years, the cost is one thing. If the system lasts 40 years, then you could have something that's significantly higher cost and still get greater value out of it. Another problem is really the self-discharge. As I said before, this is the storage charge, which dissipated through internal chemical reactions, and this is basically a loss of energy. So if you have self-discharge problems, you charge up the battery, and if you let it sit there for a day or two, some of that energy is lost. It's lost typically as heat, but then again, the energy is wasted. You can't get it back. And then finally, the round trip efficiency of the battery is really critical, which is how much energy you put in compared to how much energy you get back out. And lithium-ion batteries are very good at this, and really any systems that are being seriously considered for grid scale storage have to have these really high round trip efficiencies. So what kinds of things can you do with batteries for the grid? So one of the things is always related to money. And when it comes to energy production, distribution, and usage, money cost always comes down to it. One of the things you can use them for is arbitrage, which is basically charging the battery when the energy prices are low and then discharging it when the energy prices are high. And then you basically can make money. Because what many of you may not recognize is that on the wholesale electricity grid, basically the price of electricity changes with demands. And so basically at night times when everybody's asleep and then people aren't using very much electricity, electricity costs are low. And during the day when people are really using a lot of electricity, energy costs come high. Now, most consumers don't see this. In some states they do, but most states that's not the case. Also, you can use battery systems for load leveling, which is somewhat similar to the arbitrage, where basically you're having when there's excess electricity being generated, you can store some of it. This also can really occur with renewables. So during the daylight, you get sunlight. As Mary's presentation mentioned, using photovoltaics to generate the electricity, you can store that electricity in the battery system and then use it again overnight. So it's really very important a lot of time to couple these battery systems with renewable systems. Wind is the same way. When the wind blows, you have electricity. When the wind doesn't blow, you don't have electricity. But if you have it coupled to a battery system, you can store that electricity and use it when you need it. Also, another thing that's good with the battery systems is frequently these are very relatively high power systems, which allows you to charge and discharge rapidly, which can help to stabilize the overall grid. Because once again, you always have to, whatever production is being generated has to meet demand. And if you have some kind of flexibility with battery systems, this can really help stabilize the grid. And so where should these batteries be located? Basically, you can locate them within the transmission network. So basically, to help your peaking the capacity, help you manage peak capacity and operating reserves. Also, frequently you might want to co-locate these with generation systems of renewable systems. So, for example, if you had a really large wind farm, you might desire to put battery system, a large battery system there, coupled with the wind farms, and then you don't have a lot of transmission problems transmitting the energy from the wind farm to the battery system and then back and forth. And once again, you would probably want to do this with a large solar systems, where the large solar system would also have a coupled battery system on site to prevent you from having problems with the transmission. And then finally, I'll bring up another topic, which is in terms of battery storage for large grid scale systems is the Redox flow battery. And this is, I think, probably the next generation of battery systems. It has its own sets of problems, but it may be lower cost. And in this case, you have large tanks of liquid, which are electrochemically active liquid, and you can pump these systems through the flow cell and then basically cause electrochemical reactions where as you charge the battery, basically you flow in one direction, and as you discharge the battery, you flow in the other direction. Some of the disadvantages of these systems are they're relatively large size, and you have a required mechanical pumping of the corrosive liquids. But nonetheless, overall, in the long term, these systems may be lower cost than some of your current battery systems, such as lithium-ion systems, and we may be seeing more of these types of systems in the future. And so with that, I'd like to thank you guys for giving me the opportunity to talk. My research was supported by the U.S. Department of Energy EPSCoR program, and a lot of the information on the grid scale storage is part of the NREL Grid Integration Toolkit. And this is just a photo of my research group on our summer group outing a year or two ago. Thank you very much. And this is my building, my office. I'm right there right now. That's my office.
Thank you, Dr. Lucht. I feel like I just got a crash course in lithium-ion batteries. It was
You did.
awesome. So again, I'd encourage folks to just put some questions in the Q&A. If you can, not the chat, the Q&A would be great. We'll get to some of them now, and we'll get to some of them later. We have a couple of questions there. Where are we seeing any of these large scale battery systems, like utility scale battery systems in the US working now? And what do you think is like a approximate timeline for more widespread uptake of these types of systems to stabilize the grid?
So, I mean, I think some places you're seeing them currently are coupled with renewable systems. So in larger wind farm areas and also solar panel areas, they are putting in these systems. Another place, I mean, they have been around for a long time related to load leveling, just to kind of help balance the system. And then the other place where you're seeing them is really in a lot of remote areas, where basically some remote cities rely upon these as really part of their electrical system, where they're not necessarily part of the grid. In some of the places where they're more being introduced earlier. And in the future, I think you're going to see them all over the place. And I think once again, I think primarily as in Mary's presentation, where she showed how much grid storage is anticipated in 2050 or whatever it was. It's all, I think, primarily going to be coupled to these renewable systems, because in order to make renewables viable, you need to be able to sell the power at any time. And so I think that's where you're going to see a lot more.
Thank you. And then we also had quite a bit of interest in lithium-ion batteries are becoming more popular for all sorts of things, as you mentioned. But you did mention they have an 8 to 10 year lifespan usually for an electric vehicle.
Well, most of the current electric vehicles are being warranted for 8 years, and probably 10 to 12 year, maybe real full lifetime. So yeah, that's a concern. It's also a concern for the grid.
Yeah, so I think that we had a couple of questions regarding recycling these batteries and if they can be recycled or disposing of them and what types of issues that might cause.
Yeah, so that is a very active area of research in the battery field and becoming much more important. One of the things with it right now is it's a volume of scale thing, where the cost associated with recycling relates to how much batteries you're recycling. And so right now, since we'll say like with electric vehicles are just starting. So there aren't a lot of old electric vehicle batteries that would need to be recycled. So if they are going to last 10 years, 10 years from now is really where, because now you're finally starting to see a lot of electric vehicle sales, where you're going to start seeing that. And yes, definitely people are studying this, and it will be something that is occurring, especially in terms of the current lithium-ion battery systems have both cobalt and nickel in them, which are pretty expensive metals. And the most of the current recycling programs are really focusing on getting the nickel and the cobalt back. And, current cell phones and laptops and things, there's some recycling of those going on, but really part of the problem right now is the volumes of those materials are not that high in order to make it cost effective to recycle.
Okay, and before we move on, we've just got one more in that same vein of question asking from Tom in the audience. Is the manufacture and disposal of lithium-ion batteries more dangerous to the environment than fossil fuels, in your opinion?
More dangerous to the environment than fossil fuels? I mean, I would say probably not, because I think, once again, most batteries are still, they're not being put into the standard garbage. They shouldn't be. They should not. They should be put into these more of the recycling and storage centers, or even if they're not being recycled, they presumably are being disposed of in safe fashions.
Right. Yeah, and as we get
Yeah,
to
so
this,
don't throw away your batteries in the garbage.
thank you. I suppose as we get to the scale as well, and techniques advance, they'll become less sort of an impact on the environment there as well. Well, thank you so much,
Okay.
Dr.
Stop
Lucht.
sharing here.
That was awesome.
Thank you.
So I would now like to introduce our final speaker for the night. Jesse Deroja. He's a PhD student in the Industrial and Systems Engineering Department at URI. He's also a 2021 URI Energy Fellow. He's placed at the URI Sustainability Office. And I just also want to take a second to give a little shout out to all the Energy Fellows I see in the audience there. Thanks for being here and for supporting Jesse. Jesse's research explores efficiency and the impact of ergonomics in the solar industry. So with that, Jesse, I'm going to give you presenter privileges. You can go ahead and read, and looking forward to your presentation.
Thank you, Kaylin. I hope everyone can hear me okay and can also see my screen.
Looks good.
Thank you for this opportunity to present this research as part of the PIER lecture series. I'm a part of the Sustainable Innovative Solutions Lab at the University of Rhode Island, and I worked on this project with Fermain Karanza-Sid and my academic advisor, Dr. Gretchen Markt, and it's titled Quality Assurance and Metrics Associated with Solar Farm Production. So the main motivation for this project is the growing concerns regarding discrepancies between a photovoltaic system's actual production and its production projections over time. The Solar Generation Index in 2020 reported that over 30% of non-residential solar projects operating between 2016 and 2019 underperformed by an average of 6.3%, with a quarter of them missing their production targets by over 10%. These discrepancies between actual production and production projections can lead to unreliable projections of cost, which can then feed into a reinforcing feedback loop of loss of revenue for companies, reduction in customer and user satisfaction, and hindrance in the efficiency growth and adoption of solar. So therefore, the goal of this project was to do a preliminary analysis to work towards developing a methodology for detecting production anomalies in large-scale PV systems. We believe that being able to detect production anomalies in these systems will help in finding the root cause of any mechanical issues associated with PV systems that might be hindering their production ability and can lead to more efficient maintenance as well. So by production anomalies, we mean situations where there is a significant deviation in the production behavior of a large-scale PV system that is likely due to mechanical issues. In order to develop this methodology, we focused on two PV systems in Rhode Island, PV system R and PV system T. Our main hypothesis or assumption was that can we use two systems that have similar production conditions to be able to track the production of each other, so that if one system is not performing as it should be, we will be able to detect that through the other system. So we focused on these two systems in Rhode Island, and they are similar in size, 2.6 miles away from each other. They were installed in the fall of 2018 by the same developer, and we used winter's forecasting method to forecast what their production should be for June 2021, based on their production history in 2019 and 2020 of June. Then we used a statistical significance test called Wilcoxon rank sum test to compare the production error for each system. Production error is calculated just by subtracting the actual production by the forecasted production. And our hypothesis is statistically significant differences in the production error between PV system R and PV system T can indicate the presence of production anomalies. This slide is just to give a deeper insight into the methods that were used. And anyone who has questions about this, we can talk more after the presentation. So it was mentioned before that we forecasted the production for both systems, PV system T and R, for the entire month of June 2021, using the historical production data from June 2019 and 2020. So this is just an overview of the results for June 1st to 10. As you can see, we believe that it's a good fit. It generally follows the shape of the production curves. However, we do notice that for the higher producing days, it tends to underfit, which is something that we are very interested in looking into and improving. This is an overview for June 11th to June 20th, and an overview for June 21st to 30th. For the purposes of this presentation, we chose to focus on June 18th to 22nd to present our results on, because these days surround the summer solstice, which has great solar production potential. We see that June 18th, 19th, and 20th here had a higher production than June 21st and June 22nd. However, on June 18th, 19th, and 20th, we notice that there seems to be a peaking out of the production. This is likely due to inverter clipping, which is a phenomenon where, based on the maximum capacity of your inverter, there will be a peak in the production because the inverter is not able to carry that load. So when we look at the actual and the forecasted production, and we calculate the production error, what we expect to see is that the production error for both systems should be very similar, statistically speaking. It should not be statistically different because they have very similar production conditions. This is a plot of the production error for both systems, PV system R and T, for the days shown previously. And as we can see, for most of the time periods, the production error between the two systems is not statistically different. They seem to be following very similar distributions. However, it's clear that for June 18th and 19th, June 18th and 20th, between 11 and 5 p.m., there are statistically significant differences between the distribution of the production error. And this is likely due to the inverter clipping phenomenon that I highlighted a few moments ago. But on the production days, like the 21st and the 22nd, where we don't see the inverter clipping, we see that the production error for the two systems follow a very similar distribution. So what conclusions can we draw from this? We believe that this methodology can be used as a starting point to detect production anomalies that are potentially due to mechanical failures in the system, where we can use two systems with similar production conditions to track each other and to be able to recognize errors or production deviations in another. And in this situation, with the days considered, it worked well. Both systems, their production error was following similar distributions. However, in situations where there were mechanical issues due to inverter clipping, we were able to see those significant deviations. So the future work involves incorporating this methodology on a larger scale on systems that we know are experiencing difficulties, so that we can train the methodology to be able to identify different issues and problems within those systems. Thank you, and I'm happy to take any questions based on that.
Thank you, Jesse, for sharing that work. I'd like to encourage everybody again to throw some questions up in the chat. We do have a few questions that I'd like to get to that we didn't get to earlier. Jesse, are these types of, so for the work you're doing on these two solar fields, are there already algorithms that companies are using to predict these type of inefficiencies or that you're aware of? Or is this kind of a new field of research at the moment as solar expands?
There's definitely research being done in this area. Based on the data we had in this preliminary study, we felt that Winter's method was the most appropriate forecasting method. because literature on it is very easily accessible. There's a lot of literature on it online, and it's used to detect trend and seasonality, which solar production typically has. So there's definitely well-documented research being done in this area, but we wanted to use a methodology that will work very well for the particular systems we're focused on.
And how we have a question from the audience here for you. How accurate do you think is it possible to predict like to get 100% accuracy? Or like what is, what's the goal? Is it sort of like 90%, or is it possible that we can get 100% efficiency with these systems?
Okay. I think that's a very big question, because I think with solar, there's many ways to look at the efficiency. But I would say the goal is to be able to have a system whereby if there is a mechanical failure, we're able to detect it quickly enough and to identify the proper maintenance for it. So I would more look at it from that perspective and work towards continuous improvement and growth in that area. Okay.
Yep, that makes a lot of sense. Thank you so much. So now that we have a few minutes at the end here, I'm gonna go back to to open up some questions for any of our speakers. And we had one from earlier for Mary, and I just, as we're talking about solar, I'd like you to elaborate on this, Mary, a little bit, if you wouldn't mind. So Frank had mentioned that his solar system in Rhode Island had a payback time of about 9 years after the incentives, but if his electricity costs were half of that, it would be close to 20 years for a payback. So would you elaborate a little bit on how municipalities or state convincing people to invest in solar with longer payback times, or if that's not working?
So I put an answer back in the Q&A, but so in those areas with lower electricity prices, it may not make sense for residential systems, but if you keep in mind that price chart that I showed, residential systems are almost 3 times the cost than a utility system. So utility scale systems are less than $1 a watt. The residential installed systems are around $2.76 or something like that. And so the price difference between those two systems, you are able to install utility scale systems at a payback that the utility can recover their costs. So we're seeing a lot of power contracts, which is what we see, power purchase contracts is what they're called, or power purchase agreements. And we're seeing a lot of those where the price is at 3 cents per kilowatt hour. So if you think about your utility bill and how much that is, 3 cents for the wholesale purchase of the actual electricity. The utility, of course, adds a lot of fees onto that, but they usually can make 3 cents work, and is actually quite equitable, if not lower cost than a lot of their other options.
Thank you. We have another question up that I believe for Jesse. And I think I'm getting this here. Are renewable energy systems other than solar, so wind or other renewable energy systems, are they experiencing similar forecasting issues? And I think maybe the question is your research applicable to those other systems as well, or is specific to solar systems?
I think that's a great question. Fortunately, I'm not as knowledgeable about the operational issues with other renewable energy systems, but some of the techniques that I'm using in this presentation, I think can be applicable, because it's only based on the production history of the systems, and also finding another system or other systems in the area with similar production conditions, so that in areas where the production error in those systems is significantly different, we can assume that this might be an opportunity to look into why that is, and from there be able to identify the root cause. Is it weather? Is it a mechanical issue? And from there know whether we need to do maintenance. So I think it is applicable.
And another question we got on that topic, Jesse, too, is can you elaborate a little bit on what types of mechanical issues that you've seen that are causing these inefficiencies?
Yes. So I think a good example would be soiling, off the top of my head. So like an accumulation of dust in the area that may be causing some shading effects over time. So that would be a good example of a mechanical issue. Yeah.
Thank you, Jesse. I see we have quite a few questions that have been answered by Dr. Lucht, but if I could ask you, Dr. Lucht, to elaborate a little bit. We have a couple on looking at the scarcity of lithium and where it's coming from, and if the lithium scarcity is a real issue, is it a supply chain issue like we're seeing with other things, or if you could just talk about that a little bit.
Okay, so I would say it was a perceived issue 10 years ago when lithium-ion batteries were first becoming more widely utilized. And there's plenty of lithium on the planet for all of the applications that are really desired. The problems is really related to cost of mining and purification of the ores, and that a lot of the lithium that's currently being utilized is out of South America, because that's where a lot of the I guess the higher concentration ores are. So it's easier to mine at a lower cost. There's also a lot of lithium in Nevada, out in the western U.S. Those types of areas, I think it's related to the concentration of the deposits, are just more expensive to mine. Also, the ocean, there's an enormous amount of lithium dissolved in the ocean, and so that's another option. But really, in terms of lithium batteries, well, the issues aren't related to the amount of lithium that's available. It's really cobalt and nickel, which are currently the main metals that are used in the cathode materials. And that's really the limiting thing, more so than anything else, which is why there's a lot of research going on right now on cobalt-free cathode materials, but also, attempts at nickel-free.
Okay, thank you. There's also one other comment from Jay Edwards about his 2005 Toyota Prius.
I saw that.
And he said he's 325,000 miles on it, battery still growing strong, and you had mentioned that has a different type of a nickel metal hydride battery with a longer lifetime.
I have a Prius in my driveway too. It's got 100,000 miles on it. And I got two cars with a fully electric vehicle. My wife's got a E-Mini. It's all lithium-ion. I got a Honda Insight, which has got a lithium-ion battery too.
So you said it has a lower energy density. Can you just explain a little bit about what the pros and cons between those two might be?
So once it's just weight. So in terms of the nickel, the batteries that are in Prius, Pre-I, are nickel metal hydride batteries. They're heavier for the amount of energy you get. And so basically you would have to have a massive car that then was driving around hauling all these batteries to really have a long driving range. Well, with a lithium-ion battery, you can use a smaller battery and still get the same kind of driving range. So for example, I own a Prius and I also own a Honda Insight. Both of them are hybrids. The Honda has a smaller lithium-ion battery system in it that's underneath the seat, while the Toyota Prius has a larger nickel metal hydride battery. Nickel metal hydrides are less expensive, they last longer. So it's, but in either system, they work fine for a hybrid. But for a fully electric system, the nickel metal hydrides are just too heavy to give you the driving range you need.
All right, thank you.
But the Prius is an awesome vehicle.
Very good. Thank you very much. We have another question for Mary from Donald in the audience there. He's asking about smaller distributed solar systems like parking lot canopies and or non-solar farm ground mount systems. And are they considered potential contributors to the grid or not?
That's a great question. So we typically call those community scale systems, where it's smaller than the utility scale, massive, megawatt scale type of systems, but they're not on the roof, and so they're ground mounted, and they're typically anywhere from 100 kilowatts to maybe a megawatt, and they can be grid connected. But we are seeing a lot of, I shouldn't say a lot, but many of these being installed in what we refer to as microgrid systems. So if a community wants to establish themselves in a microgrid system, then they have their generation and their grid capable of disconnecting from the central grid system. So they basically are creating a mini grid within the bigger grid community. So in that instance, I don't know if it's directly connected to the central system. It can be, but it also doesn't have to be. So typically they are connected to the grid, but they don't have to be if you're trying to establish a microgrid system.
Great. Thank you. And I do have a couple of questions. I want to go back from our first talk with Dr. Lin. There's a couple of questions on the cybersecurity attacks that you mentioned. So first, how frequently are these attacks taking place? And, is that being monitored or recorded? Is there some research being done on how often and to what extent these attacks are taking place on the electric grids or the smart grids?
Unfortunately, actually, for the complete set of attacks, especially on the power system, it's very hard to track in the detailed number, because for the reason is that for some of the company, their system is under attack. To protecting their company's reputation, they will not be willing to releasing this type of information. However, there are some research and there are some even some industrial research and some research in university will catching some of the activities, malicious activities that is performed initially by the attack, which is not a complete attack. It's just type of malicious activities, which we call it probing different type of machine to see what type of system you're running, what type of software you're running, and based on this information, they can decide what to do next. This type of information actually has been continuously recorded by some of the university. One of the leading universities is from the University of Michigan and Ann Arbor. They have a research group has been tracking this type of activities almost for 10 years.
And had another question about preventing these attacks. And now that there's some research being done about what's going on, who are the responsible parties for preventing them? Is it government, utilities, companies, or on the individual level?
Wow, that's the question actually beyond the scope of my understanding, because it's not some of the answer to this question is actually not coming to the engineering. It's actually coming from a lot of policymaker and some of the utility companies, system administrators. I think my understanding is that it needs to involve all, because researchers can provide some of the solutions, but in many cases, the policymakers also need to put in some of the effort to apply those type of cybersecurity solutions. And one factor that can affect this type of deployment is that on the power system is a very unique system compared to the general purpose system. On general purpose system, if you isolating the computer devices from the network, it actually can kind of make it safe. But for the power system, if you're isolating one resource, one devices from the power grid, maybe if they isolated from the network, that's okay. But if they're isolating that area from the power grid, that's actually equivalent to causing a blackout, which is what attackers want anyway. So in these cases, this is the type of situation that we call the power system is not a fail-safe system. So it requires a little bit more different type of reaction when the cyber attacks happen.
All right, thank you. And we've got just one more question, and I like to leave this, so somebody can have a take-home message. Are there any steps the average person can take to prevent themselves from being susceptible to these types of attacks?
I think that one of the very common things that you can, actually I can think about three things that you can do every day, but which is very easy. First is do not click on the link from the spamming email. And many of the email boxes do a great job to classify some of the spamming email in your mailbox. And second is that always enable the two-way authentication. Third way is that including those special characters in your password. All those type of characteristics, researchers find that this can actually significantly increasing the level of protection, like adding one level of the one special characters can significantly increasing the time for the attackers to make a guess of a password. The two-way authentication can also significantly increasing that your system has been compromised, and also spamming email has been one of the major sources for the attacker to penetrate into some isolated communication networks. And one interesting experiences of the spamming email is like few years ago, there's in a university, there's a IT department kind of sending a notice to everybody in the campus, say that directly say that this email contains malicious link, and please do not click on this link. And there's still like around 20 people click on it anyway.
All right. Well, I think that's some very practical advice for us to take away. So I think we have one final question in the chat here. I believe it's for Jesse. Just because we have a couple extra minutes. Does weather factor into the output calculations for PV systems?
Yes, I think weather is always a factor for PV systems. With any calculations that we're doing, it's important to consider the effects of weather, because when it's a cloudy day, you see changes in production. When it's sunny, when it's cold, it all affects the production. So it's very important to take weather into account.
Right. Well, thank you very much. I believe we've answered most of our questions, and so we can go ahead and wrap up a few minutes early. I just want to say thank you so much to everybody for participating, for all of your wonderful questions. Special thank you to our speakers from URI and Mary from NREL. We really appreciate you being with us. I'm just going to wrap up the evening with a reminder that tonight's lecture will be available on the URI Cooperative Extension YouTube channel, so you can watch it again or share it with your friends. And please make sure to complete the post-lecture survey. We really do read them, and they are useful. So you'll be getting a notification about that just after we end the evening tonight. So thank you very much, everyone, and have a great evening.
Thank you.